all our basic tools for derivatives, we can look at some problems with derivatives and try to answer them. So question. If f and g are both, if f plus g is differentiable at, let's say, a, are f and g both necessarily differentiable at a. Differentiable at a. Answer. Well, we have seen that if f and g are differentiable at a, then f plus g is differentiable at a, but it need not be true the other way around, right? The easiest example is take a non-differentiable function at a, okay? Let f of x is equal to absolute value of x, right? And g of x is equal to negative absolute value of x, right? Then f and g are not differentiable at 0. We know that they have a corner at 0, so they're not differentiable at 0. Does this, but f plus g of x is just constantly 0, is differentiable at 0. So no, it doesn't need that need to be that if f plus g is differentiable at a, both f and g are necessarily differentiable at a. Another question that we can ask is if f is differentiable everywhere, if f is differentiable everywhere, does f prime need to be continuous everywhere? Or can there be a point a where, oh, even if f is differentiable at that point, f prime is not continuous at that point? Answer. You have actually already seen the counterexample, though we haven't, you didn't probably work it out completely yet, and it's slightly non-trivial thinking of it, right? Even if you know about integrals, you might have some basic idea of saying, oh, if I need it not to be continuous at one point, let me take a jump somewhere, right? Let me think of a function which has a jump. Maybe let's think of a function which is -1 till 0 and 1 till 1 from 0 onwards. If you integrate the function, you're going to get absolute value of x, right? And at the very specific point 0, it is not actually differentiable, right? In nearly every case that you're going to think of, that is the same thing that will happen. It's hard to come up with such a function, but here's a function that works. Let f of x is equal to x squared sine 1 or x when x is not equal to 0, 0 when x is equal to 0. Okay. Then we have seen, or it is easy to say, it can be shown from the definition of the derivative, that f prime of 0 is exactly equal to 0. Now f prime of x is equal to derivative of x squared sine 1 over x when x not equal to 0. When x is not equal to 0, f prime of x is equal to 2x sine 1 over x plus x squared cosine 1 over x multiplied by negative of 1 over x squared, right? Which is equal to 2x sine 1 over x minus cosine of 1 over x. And now it is easy to see that this function is not even defined at 0. Well, and in fact, limit x goes to 0, f prime of x is equal to d and e. This limit does not exist. Therefore, in particular, limit x goes to 0, f prime of x is not equal to f prime of 0, and hence f prime of x is not continuous at 0, even though f of x is differentiable everywhere. Now, you can see it is a problem on your next homework for chapter 9 that, in fact, if the limit if limit f prime of however, if f is differentiable everywhere and limit x goes to, let's say, a f prime of x exists and is equal to L, right? Then f prime of a is equal to L. Okay, so if it is differentiable and the limit is equal to L, then f prime of a has to be equal to L. It can't be that, oh, your limit is different than the value if the function is differentiable and the limit exists. Okay,